Now let's take a look at applications of linear systems.
Now basically these are word problems involving the linear systems of equations that we've been working with and that we know how to solve now by three techniques, right? By graphing, by substitution, and by addition, right? Three techniques that we use in Chapter 6 to solve linear systems. Let's look at the word problems associated with these. So really no new material here except the word problems and how to set them up. Right? Let me do a few examples and then give you some problems to try and post it onto this discussion area in Blackboard. All right. Now let's look at two types of problems we'll deal with in this section here. All right. The first type of application problem we'll deal with are distance problems, or uniform motion problems. All right. Uniform motion. And that involves what? An object in motion. Except here, we'll deal specifically with two types of uniform motion problems. The first type we'll deal with are called rate of wind problems. Rate of wind problems. And the second type of uniform motion problems we'll deal with is very similar to rate of wind, except it'll be called the rate of current problems. Okay, so these two problems involve the distance formula where distance is equal to what? Rate times time, if you recall. All right. Now, what's a rate of wind problem? Well, it involves what? An object that is going with the wind or going against the wind. And you want to find out how fast it can go when there's no wind or calm air. And you also want to find out how fast the wind is blowing it. All right. Similarly, for the rate of current problem, now you're in the water. You're on a river, for example. All right. And you want to find out, okay, how fast can a boat go when there's no current? That means in still water or calm water. And how fast is the current flowing at? How fast is the river current? Okay. So we answer questions like that in these two types of problems here. And we'll look at some examples in a moment here. All right. And the other second type of problem we'll deal with are more challenging. Let me call these the general two-variable problem. So these problems involve two variables here, general two-variable problem, namely x and y. All right, and then we get two equations, two variables, and then we can solve them by either the substitution method or the addition method is what we'll use here in this section here. All right, so let's look at, without further ado, let's go and look at the first type. Let's look at the uniform motion problem. Let's look at the rate of wind problem first. All right, and let's look at this example here. Let me go clear out the screen. Okay, so let's look at this problem right here. All right, this problem says what? A plane flying with the wind flew from LA to Chicago a distance of 2,250 miles in 5 hours. Flying against the wind, the plane could only fly 1,750 miles in the same amount of time. Find the rate of the plane in calm air. That means how fast is the plane when there's no wind. And the rate of the wind. How fast is the wind blowing it? All right? So that's a typical rate of wind problem on the homework. Right? But so let's use the uniform motion table we have to set this up. So let's make a nice big table here, if you will. Let's do the best you can here. Okay, so make a table with 3 rows in it. All right, and a few columns here. So let's put the equation in. Rate, all right, times time, okay, equal to what? Distance. Okay, so we've seen this equation, but r times t is equal to d, right? So no big deal here. All right, what goes into these two boxes? Well, for these types of problems, it's your two situations. We have two situations here, right? We have a plane flying with the wind, and we have it flying against what? Against the wind. So let me say with the wind, and against the wind. Okay, so with the wind, against the wind, all right? So two situations, with the wind, against the wind, okay? Now, what is the rate in this case? Well, now I want to know two things here. I says what? Find the rate of the plane in calm air and the rate of the wind. So these two things will be my variable here, all right? Okay? Let me let R be the rate of the plane, all right, in calm air. All right. So R is the rate of the plane in calm air. That means what? That's the speed of the plane when there's no wind at all. All right. Let's let W be the rate of the wind. because these are the two things I want to find out, rate of the wind. So the question is asking for the rate of the plane in calm air and the rate of the wind. Let those be R and W, since I don't know what they are. Introduce two variables here, right? Now, here the variable these variables go in the rate column because they're rates here, all right? Now, in terms of R and W, let's think about this now, all right? If you're going with the wind, all right, how fast can I go? So R is my speed without any wind. W is the wind. If I'm going with the wind, does it make sense that the wind is helping me go faster if I'm going with the wind? Hopefully it does. So therefore the rate of the plane going with the wind is what? R plus W. Can we see that? Again, if you're going with the wind, you're going faster because the wind is helping you out. So your speed is tacked on to the wind speed. So R plus W. On the other hand, if you're going against the wind is slowing you down. So my rate will be R what? Minus W. Can we see that? We're being slowed down by the wind when we're going against the wind. Okay? So, what is the time situation then? Well, what do we know about that? Well, it says what? A plane flying with the wind flew from LA to Chicago, a distance of 2,250 miles in 5 hours. So with the wind, we flew 5 hours. So 5 hours with the wind, all right? Flying against the wind, the plane could only fly 1,750 miles in the same amount of time. So that's what? 5 hours also against the wind, all right? So we flew 5 miles with the wind, 5 miles against the wind. So the distance is just rate times time. So again, the last column is what? Multiplying the first two columns. So this is 5 times R plus W, distance with the wind, 5 times R minus W, distance against the wind, all right? But we know what these two distances are. The first one is what? 2,250. The second one against the wind is what? 1,750. So therefore, my two equations that I come up with here are what? 5 times R plus W equal to what? 2,250, distance with the wind. And 5 times R minus W, that's the distance against the wind, that's equal to what? 1,750. All right? Can we see that? So we get these two equations here and two variables, which I can now solve by either substitution method or addition method, all right? Now, let me go ahead and solve it this way here. Let me do a slight twist in the algebra. Because notice that both of these numbers, both sides here, can be divided by what? Divided by 5, right? 2250 is divisible by 5, as is 1750. So in both equations here, I can divide out the 5's before I continue. That will make my numbers a little smaller. Now, let me do that if you don't mind. So let me recopy the first equation. 5 times R plus W equal to, I'm just doing the algebra to solve this system now, right? The setup part is done, as you can see, right? Once you get to this step, hopefully you can finish the rest of the problem, all right? That's equal to what? 2250. Let me divide both sides of the equation by 5, as I mentioned, because that will divide out this 5 here. So I get R plus W equal to, what is 2250 divided by 5? Punch it down to the calculator. I get 450. Hopefully you see that. And like similarly here, let me divide both sides by 5 here. Let me do it right here. So we get, and let me write the results down here. So I get R minus W equal to what? R minus W is left over here, okay? And what's 1750 divided by 5 on the calculator? That'll be 350. So that's equal to 350 from the calculator. All right? So look, I have a nice linear system here I can solve. And obviously you see the addition method being the best technique here because W's will what? Cancel out. If I simply add these two together, the W's drop off. So R plus R is what? 2R equal to what? 800 here. Okay? So R is equal to what? Dividing both sides by 2. 400 miles per hour. All right? So that means the rate of the plane in calm air when there's no wind is 400 miles per hour. What about the rate of the wind? What's W then? Well, how do I find that? Well, just plug it back in. Plug into one of these simplified equations. I mentioned you could plug it into the modified equations, right, in the previous section. So let's plug 400 in for R here. So I get R plus W is equal to 450 here from this equation right here. All right? And R is what? 400. So 400 plus W is equal to 450. All right? Subtracting 400 on both sides here. So we see that W is equal to what? 50. So W is equal to 50 miles per hour. That's what? That's the rate of the what? Rate of the wind. So the rate of the plane in calm air, 400 miles per hour. Rate of the wind, 50 miles per hour. And that's our solution. Okay, so hopefully you see the setup here is not too bad. Now the setup for the rate of current problem is identical to the rate of wind problem. Let's go ahead and show you that one. All right, let's go ahead and let me clear out the screen here, if you will. Okay, let's take a look at a rate of current problem. All right, let's take a look at this problem. Paddling with the current, a rowing team can go 48 miles in 4 hours. Against the current, it takes 6 hours to go the same distance. Find the rate of the rowing team in calm water and the rate of the current. So again, how fast can this team go when there's no current, and that means calm water, and how fast is this river flowing at? What is the rate of the river, rate of the current in the river, correct? So again, let's set up using the uniform motion table here. Take our time on that, and let's make a table with 3 rows in it once again. All right. So again, rate times time equals distance. Okay, so not too bad. All right, what goes in these 2 columns? Well, similar to the rate of wind problem, right? Here we're going with the current, so to the 2 situations. With the current and what? With the current and against current. All right, so here let me put with current. All right, and against current. All right, with current and against current. All right. Now, again, I want to find 2 things. Rate of the rowing team in calm water. So let me introduce a variable R. Let R be the rate of rowing team in calm water. Okay, clearly identify your variables. This is how fast we can go when there's no current. All right, and let's let C be the current. All right, so instead of W be the current, let's let C for current. Okay, rate of current. Okay, just like we did set up with the rate of wind problem. Again, how fast are we going if we're going with the current? Well, if I'm going with the current, that means the current is helping me go faster, right? So it's going to be what? R plus C, all right? If I'm going against the current, well, the current is slowing me down. So R minus C, just like we did with the rate problem. R plus W with the rate of wind problem. R plus W, R minus W, right? Same thing, same concept. So the setup for the rate of current problem is identical, basically, to the setup for the rate of wind problem. Okay? Let's look at the time situation. How much time do we spend going with the current? How much time do we spend going against the current? Well, what do we know about that? It says here, paddling with the current, a rowing team can go 48 miles in what? 4 hours. So with the current, we went what? We went 4 hours, all right? Against the current, it takes 6 hours to go the same distance. So against the current, we went for 6 hours, all right? So what is the distance with the current? Again, just multiply to get that distance here. 4 times R plus C, all right? Here, 6 times R minus C. Can we see that? Okay, so that's the distance with the current. That's the distance against the current. And we know what that is. It says here we went 48 miles with the current. So 4 times R plus C is equal to what? 48. Similarly, it says what? Against the current, it takes 6 hours to go what? The same distance here, right? That means we also went 48 miles, but we did it in 6 hours this time. So it'll be what? 6 times R minus C equal to what? 48. All right? And once again, like the previous example, 48 is divisible by 4. And 48 is also divisible by what? By 6. So let's divide out. Divide both sides by 4. In this case, let's simplify this equation. 4's drop off. So let me put it here. R plus C is equal to what? 40. Oh, sorry, not 48 here. 40 divided by 4 is what? 12. My apologies there. Here, divide by 6 here. Okay. 6 is drop off. So I get R minus C left over. So R minus C equal to what? Equal to 48 divided by 6 is going to be what? 8. All right. Again, I can solve this linear system by the what? Addition method, by adding them. C's drop off. R plus R is 2R equal to 20. So therefore, R is equal to what? 10 miles per hour. Okay, dividing both sides by 2. So the rate of the rowing team is what? 10 miles, 10 miles per hour. All right. So in calm water, that means when there's no current, we can go 10 miles per hour. How about how fast is this current then? Well, again, let's plug it into the first equation here. All right. So it was what? R plus C equal to 12, right? I just found R to be 10. Plug it in. So 10 plus C is equal to 12. Subtract 10 on both sides. Hopefully we see that C is equal to what? Equal to 2 miles per hour. Right? So the rate of the current is 2 miles per hour. Rate of the rowing team in calm water, 10 miles per hour. And we have our solution here for both parts of the question. Okay? So again, the setup is identical to the rate of wind problem, and make sure we can solve the linear system that results once we set it up here. Okay? So let's go and try the more challenging problems. Let's look at the general two variable problems that we have as well in this section. Let me paste another question here. Let me clear this out. Okay, let's look at this problem right here. So here's a more challenging problem for us, right? Let's look at this one here. The manager of a discount clothing store received 2 shipments of clothing. The cost of the first shipment, which contained 10 identical sweaters and 20 identical jackets, was $800. All right. The second shipment, at the same prices per jacket and per sweater, contained 5 of the same sweaters and 15 of the same jackets. All right. The cost of the second shipment was $550 total. Find the cost of 1 sweater and 1 jacket. All right. So again, let's let that be X and Y, namely, right? So I'm going to find those 2 things. So let's introduce what 2 variables here. All right. So let's let X be the cost per what? Per sweater. So clearly identify your variables, and let Y be the cost per what? Per jacket. Okay, I want to find out what those 2 things are in this problem. As you can see, find the cost of 1 sweater and 1 jacket. That's X dollars per sweater, Y dollars per what? Per jacket. Okay. Now, let's break this problem down into what? Into 2 shipments here. All right. Let's look at the first shipment. This one's a little more challenging here. There's no set way to set it up, but the key is to identify the 2 situations and get equations out of them. All right. For the first shipment, we shipped what? We shipped 10 identical sweaters and 20 identical jackets. So 10, let me just say 10 sweaters and what? And 20 jackets. All right? Okay then, so what does that mean then? Well, if it costs X dollars per sweater and we bought 10 of them, what's the cost going to be? Well, 10 times X, right? So this will be 10X here. If we bought 20 jackets and it costs Y dollars per jacket, that means it's going to be 20Y for the 20 jackets here, right? So it's going to be 10X plus 20Y being our total cost here for the first shipment. And how much did we pay for this first shipment? $800, right? So that's equal to 800, as you can see. Okay, so that's the first equation here, right? Let's look at the second shipment. Let me write it up here to save space here. All right, second shipment, we have what? 5 of the same sweater, 15 of the same jackets. So we have 5 sweater. That means what? The cost for that is going to be what? 5X, right? Because X is the cost per sweater. And we have what? 15 jackets. What's the cost there? Well, Y dollars per jacket. So 15Y. So the equation I get from the second shipment is going to be 5X plus 15Y. The total cost there is going to be what? Cost of the second shipment was what? 550. So $550, as you can see. Okay? So we get these 2 equations here. Now, once we get these 2 equations, it's a matter of solving them, right? So now before I do that though, once again, notice that for this equation here, all right? So again, the word problem part is over, right? I set it up already. Now it's a matter of solving the system either by substitution method or what? Addition method, all right? So, excuse me. So these 3 numbers are all what? Divisible by 10. Can we see that? So let me divide everything by 10 to simplify, to lower my numbers down, make it easier for me, right? We don't have to do it this way, but it's just easier algebraically if I lower my numbers. So 10s drop off, so I'm dividing both sides by 10 basically. Divide everything by 10. So I get X plus what? 20 by 10 is 2, 2Y equal to 80, right? 800 divided by 10, 80, all right? Likewise here, dividing by what? 5, right? Everything is divisible by 5. So make sure we see that. 5's drop off, I get x plus what? 3y equal to 15 over 5 is 3, and 550 divided by 5 is what? 110. All right? Not too bad. Let's put my equations together now. Let me copy this equation below here. So x plus 3y equal to 110. So I'm putting my two equations, one on top of the other. All right? Now, let's solve this by addition method. Okay, let's get rid of the x here. It looks easiest to get rid of the x. All right? Let me multiply the first equation then by -1 to get rid of the x. Okay, so multiply by -1 to both sides. Again, hopefully we see that for the addition method. All right? So -1 times x is what? Negative x. Let me put it below here. -1 times 2y, negative 2y. 80 times -1, well, that's -80. All right? So if I simply add these two equations together, the x's drop off. Here I have 3y minus 2y. That's just 1y, which is great. I don't have to do any more solving here. It's equal to what? $30. All right? Okay? So y is $30. That means what? That's the cost per jacket. So cost for one jacket is $30. What is the cost for one sweater then? Well, let's go back to one of these modified equations here, all right? Let's look at this one. X plus 3y is 110. Well, I just found y to be what? To be $30, right? Let's plug that in. So x plus 3 times what? 30 for y equal to 110. So x plus 90, 3 times 30 is equal to 110. Subtract 90 to both sides. So x is equal to what? Well, that's going to be what? $20. So it costs what? $20 per sweater and $30 per jacket. All right. So obviously the prices are going up these days on clothing as well. Okay. So again, $20 per sweater, $30 per what? Per jacket. So is it $20 per sweater cost of one sweater and $30 per jacket, cost for one jacket. That's our solution here. Okay? So again, we broke this problem up into what? First, we identified the variables here. I want to know the cost of one sweater, call that X. I want to know the cost of one jacket, call that Y. And we broke this up into two shipments, and for each shipment, I'm able to get an equation out of it, and then solve the system of equations here. Okay? Let's try another one here. Let's put out the screen. Let's look at this problem right here. All right, let's take a look at this problem. The total value of nickels and dimes in a coin bank is $3. If the nickels were dimes and the dimes were nickels, in other words, if I switch them around, if I switch the number of nickels and dimes around, then the total value will change. It would be what? $3.75. So find the number of, but I want you to find the actual number of nickels and dimes in the coin bank, and the actual number should total what? $3 here. All right. So again, two things I want to know: number of nickels, number of dimes. Let's call that, if you don't mind, let's call it N and D, all right? Let N be the number of nickels, and D be the number of dimes in this coin bank, all right? Not too bad. Okay, now, if you remember the coin problems here, if I have N number of nickels, all right? What is the value of that? Well, the value would be what? 5N, right? Because each nickel is 5 cents, right? What is the value of D dimes? I have D dimes, right? D is the number of dimes. What is the value of that? That's 10D. Can we see that? Right? Because 10 cents per dime, and I have D of them. Okay? So let's go ahead and look at that. The total is $3, right? But we're working in cents, so therefore, for the coin bank here, it's going to be what? So for my coin bank, it's going to be what? 5N plus 10D is equal to what? $3, right? But that's 300 cents. Because I'm working in cents to avoid the decimal. Okay? So $3 is what? 300 cents. Just like we did for the coin problem. Check the notes on that. All right? Back in chapter 4. Okay. Now, here's the key statement here. Again, if the nickels were dimes and the dimes were what? Were nickels. What does that mean? That means instead of having N number of nickels, let me say I have n number of dimes. And instead of D number of dimes, how about D number of nickels? Okay, so again, let's look at the hypothetical situation. So hypothetically speaking, what happens if I switch the number of nickels and dimes around? Okay, so here hypothetical, n is the number of, not nickels now originally, right? Number of dimes now. Again, if nickels were dimes, dimes were nickels. Switch them around. D is now what? Not the number of dimes in the hypothetical, is now the number of what? Nickels. Okay? Well, again, let's calculate the value. Value of n dimes. Now, n is the number of dimes now. Keep that in mind. So it'll be 10n. D is now the number of nickels. What's the value of that? Well, 5D. Can we see that? All right. Again, the hypothetical situation says what? We're going to switch the two numbers around. Nickels were dimes, and the dimes were nickels. Then we have a different value of 375. All right. So instead of n number of nickels, we now have n number of dimes. The value of that, 10n. Instead of D number of dimes, we now have D number of nickels. The value of that, 5D. All right? So therefore, the equation we get here in the hypothetical situation is going to be what? 10n plus 5D is equal to what? $3.75, 375 cents. All right? So basically, this problem boils down to these two equations here. Can we see that? The coin bank, the actual number of dimes and nickels, all right, and the hypothetical situation when we switch the dimes and nickels around in terms of their numbers here. Okay? Now, let's go and do the mathematics to solve this system here. So again, I can reduce my numbers on this equation by dividing by what? By 5. Let's do that. Simplifies the numbers, makes things easier to work with. Okay? Though with the calculator, this is not too bad. So n plus 2d is equal to what? 300 divided by 5 is what? 60. All right? And here, again, I'm dividing by 5 once again. Okay, so 10 divided by 5 is 2n plus d equal to what? 375 divided by 5 on my calculator, 75. Okay, so let me put this equation right below here. So 2n plus d equal to what? 75 here. Okay, let's solve the system. Again, let me solve by addition method. You can cancel the n and the, or the d. It doesn't really matter here. Let me choose to cancel the n here, if you don't mind. Okay, so again, you take your pick. To get rid of the n's by addition method, I need to get this n to be a negative 2n. Right. So let me multiply this equation, if you will, by that, by negative 2 to the left side and negative 2 to the right side. Just using the addition method here. Right. So this equation, the first equation modified, becomes what? Negative 2n, which is what I want. Negative 2 times 2d is negative 4d. All right. And 60 times negative 2 is going to be what? Negative 120. All right? If I simply add these two equations together, the n's drop off, which is what I want. D minus 4d is negative 3d, equal to 75 minus 120 is going to be what? Negative what? Negative 45, right? So let me just check that in the calculator real quickly. Yeah, negative 45. Just want to make sure I get the right number for you there. Okay, so dividing both sides by negative 3, then we have our solution for the number of dimes. D is what? 15. Okay, so we have 15 what? Again, D represents what? The number of dimes. Those things is down here, right? It says find the number of nickels and dimes in the coin bank. This is the actual number in the coin bank. This is the what? Hypothetical situation. Okay, so don't get confused here. All right? 15 dimes is what we actually have here. All right, so 15 dimes. All right. So how many nickels then? Well, again, what's n? Plug it back in. So D is 15. So let's use this equation since I have it right here on the whiteboard. So 2n plus 15 is equal to 75. I'm running out of space here. So subtract 15 on both sides. Again, gotta skip some steps on the algebra. Hopefully you can see it though. 2n is equal to what? 60. All right. 75 minus 15. So therefore, n is equal to what? Dividing by 2. That's going to be what? 30. Okay. 30 what? 30 nickels. Because n is the number of nickels originally. All right. Well, let's test that. So if I have 15 dimes and 30 nickels, then do I have $3 as claimed in the coin bank originally? All right. Well, let's see. 15 dimes is $1.50. 30 nickels is what? Also $1.50. So $1.50 and $1.50 is going to be what? Exactly $3. So 15 dimes, 30 nickels is the correct solution here. Okay. Now, what happens if I switch it around? Just look at the hypothetical for a second here. All right. So instead of 15 dimes, let's say I have 15 nickels. 15 nickels is what? 15 nickels. 15 times 5 is what? 75. So that's 75 cents, right? 15 nickels, right? If I switch those two things around in the hypothetical situation. 15 nickels is what? Again, D number of nickels in the hypothetical. So that's going to be 75 cents. 30 dimes, $3. So $3.75, total of what? $3.75. So this answer, as you can see, does make sense here to us. Okay. But again, try to break up the problem into two situations and get an equation for each situation, like I did here, and then be able to solve a linear system of two equations here and two variables. All right. So these problems can be challenging. It does take some practice. You may have to read it more than once. All right. But let's go ahead and give you some problems to post the answers to on Blackboard here. So let's go and try these two problems here and post the answers to them in Blackboard. Okay. Let me go ahead and clear out the screen. Okay, so let's go and post the answers to these problems. Okay, so post the answers in the discussion area on Blackboard for these two questions right here. All right. A jet plane flying with the wind flew 2,400 miles in 4 hours. Against the wind, the plane flew only 2,000 miles in the same amount of time. Find the rate of the plane in calm air and the rate of the wind. So that's a typical rate of wind problem. All right, so review the setup on that. All right. Number two coin banks contain only dimes and quarters. In the first bank, the total value of the coins is $3.90. In the second bank, there are twice as many dimes as in the first bank and 1/2 as many quarters as in the first bank. All right. Now, let's look at the total value for the second bank. The total value of the coins in the second bank is what? $3.30. And you're asked to find the number of dimes and quarters in what? The second bank here. Okay? So make sure we read the question carefully. This one's a challenging problem. We'll discuss these two word problems in class. Okay? So until next time then, I'll talk about these problems in class here. Okay? So take care of it. Okay, bye-bye.